So let me continue with a parameter estimation. So non-random parameter estimation. We want the best estimates. So best estimate is minimizing the variance, or with the minimum variance. So one property we decided is that we want an unbiased estimate. That means expected value of theta hat is theta. So remember, there is no big optimality reason for that. It makes complete sense, right? Because something is unknown. So whatever is your estimate, at least on the average, that should equal what you are looking for. And then what we also learned last week is that whether so generally getting an estimator, of course, is an art, and you may or may not be able to find an unbiased estimator. But whether you can find it or not, there is a result which says that this minimum variance satisfies certain. So what it says is that whether we can find the estimator or not, its variance always is going to be greater than the Cramér-Rao bound for that particular parameter. Okay. So this is the Cramér-Rao bound. So I wrote two expressions for the Cramér-Rao bound, right? You missed this? Sorry? All right, very good. So this is sigma squared CR theta. Either you can do it as, so once again the likelihood function is so log of the joint density function. Derivative with respect to the parameter, absolute value squared. So of course the whole thing is positive. Or this is also equal to expected value of the second derivative of the logarithm of the same density function. Of course, all this density function is a function of theta also. Same thing here. So you can use either one of the expressions. And so if you get a situation where the variance of theta hat x equals the Cramér-Rao bound, then you call this to be an efficient estimate. Remember, it's a property of the. So of course this is the best that can happen, right? Why is that? Because this says that no estimator can have variance better than the Cramér-Rao bound. So if you can find an estimator which is which is efficient, then that's the end of the line, right? So then we also said a small theorem, right? All right, so I went through this. The condition for efficiency was what is it? D log of f, the joint density function, derivative is to be some proportional to Tx minus theta. On the other hand, so this is the condition for efficiency. Now, on the other hand, the condition for ML is the same thing on the left side. Equal to 0. So these two together, here you put theta equal to theta hat ml. So you put theta equal to theta hat ml, so you get theta hat ml is also Tx. That means your estimator is also the maximum likelihood estimator. Actually, a little more is true. Look at this. Also, you know that remember, we also know that the joint density function is of this form, right? So from here, you see log of fx remember, this is not a function of theta. Let me put subscript S. S is remind that it is sufficient statistics. So if I take the derivative of this, you can write another line. That's the same as the derivative on this side. So that's going to be simply d by d theta of log g theta. But this only appears as, the data appears only as in terms of Tx. Right? So equate this now, theta equal to theta hat ml, solve equal to 0. So it is easy to see from here that when you solve this, you are going to get, here this is only a function of Ts, right? Data appears only in the form of Ts. Why is that? Because remember, factorization theorem. If a factorization theorem says the joint density function can be written as the two factors. First factor independent of theta, second factor depends on theta, but then the data appears through only a function t, right? So when you solve for it, you are going to get theta hat ml as some function of Ts, right? From here, because Ts is the variable here when you solve it, right? So you also get a new result if you want. So what it says is, when everything is going good, everything works out. The maximum likelihood estimator in that case will also turn out to be a function of the sufficient statistic. So if there is an efficient estimator, it is also the maximum likelihood estimator. But the maximum likelihood estimator independently from here is a function of the sufficient statistic. So ML estimator is a function of sufficient statistic. All right, so this is the property of an ML estimator. It's a function of the sufficient statistic. But if it is an efficient estimator, then the unbiased estimator is going to be a function of the sufficient statistic. Okay? Hello? All right, so this is about Cramér-Rao bound. Hopefully you have done all the 4 problems or 4 or 5 problems. I did bring you the solutions. So there are some cases where estimator is efficient, some cases where estimator is not efficient, etc. Right? Now in some problems, the Cramér-Rao bound is a little difficult to compute. So today I want to do 2 topics. One is a little generalization of the Cramér-Rao bound. That's called, or a relaxed Cramér-Rao bound. It's called modified Cramér-Rao bound. I'm going to give you some notes, and then I want to address the question. I want to go back to, so before we do the modified Cramér-Rao bound, let's continue with the, so the Cramér-Rao bound is here. Okay. So efficient estimator, I have written all this down, I just want this one line. X is if and only if, too much noise. So if this condition is true, okay. All right, so the next question is, what if there is no efficient estimator? So remember what is, so you have sigma squared CR here, and we are able to find an estimator whose variance is equal to Tx. So this is the efficient estimator case. So then nothing more to do because we found the best estimator. Because Tx is efficient. Now look here. So here you have variance of T1x. This is variance of T2x. This is variance of T4x, etc. So all these variances are higher than the Cramér-Rao bound. Of course, T1 is better than T2 because the variance of T1 is smaller than variance of T2. But still, but still there is a gap between T1 and the Cramér-Rao bound, right? So the question is it possible, you being clever, to reduce it, to close this gap? How much is it possible to find another thing here? Can we come closer, etc.? So the question here is how to find the best estimator. So in fact, this leads us to the concept of this unpronounceable word, uniformly minimum variance unbiased estimator. All right, so that makes sense certainly, right? That's what we have been after. Hello? An unbiased estimator with the minimum variance. That's so I'm going to show that estimator like this. So this is our question. And once this is done, you can see we can sort of close this. There is a closure to this line of thinking, right? So because of, rather than rewrite all this, I'm just going to make the symbol notation. Okay. So when I write T naught, remember, this is just to remind you that any estimator is going to be a function of the data. So I'm simply, remember I used T naught earlier for about half an hour back I used it for sufficient statistic, but I'm running out of symbols, so we are talking about this quantity now, okay. For here onwards, when I say T naught, at least for our current discussion, I mean this quantity, an estimator for theta, which is the unbiased and the minimum variance. So how to find this is our code. So that's, let me finish that. And then I will I'll do some examples. But if you want a motivation towards that, hello, someone just note this down and give it to me in a piece of paper so that you also have this. So if you want a motivation, let's do a problem before I come to that one. Say xi's are normal with mean mu variance sigma squared. So remember our standard problem, mu is unknown, sigma squared is known. All of them are independent observations, identically distributed, and you have n observations. We have gone through all this. Anybody remembers what is the best estimator for mu? Yeah, there's x bar, right? X bar is 1 over n x. We went through all this, right? This is an efficient estimator, and it's also maximum likelihood estimator. And it, as you can see, it's a function of the sufficient statistics we just proved. And if you remember, this is also, because it is linear summation, this is mean with mu and variance. Variance what? All right, sigma squared, that's good. And if you remember, the logarithm of the density function is log of square root of 2 pi sigma squared minus xi minus mu, the whole squared over 2 sigma squared. So if I take the derivative with respect to, so let me call this L, 1 with respect to mu, of course I get minus xi, right, over sigma squared, right? And if I do one more time, derivative of this with respect to mu is sigma xi over sigma squared. Yeah, this is a constant. So the minus, this is, so this is, you can, if you want to write like this is minus n mu, right? So it is minus this, right? So from here you can see that sigma squared CR for mu is 1 over this, expected value is the same thing, so sigma squared over n. But you see, this quantity also has variance sigma squared over n. So this is an efficient estimator, right? So this estimator is efficient. It's also the maximum likelihood estimator, because any efficient estimator is maximum likelihood. It's also a function of the sufficient statistics. If you recall, this is the sufficient statistics, right? So everything is going good for you, okay? Now let me, same problem, but let's say that, so this is where the common sense doesn't work in statistics. For example, suppose I say, so previously theta equal to mu is the parameter of interest here. So what we just proved is that this estimator is efficient. Right? All right, now you could say, all right, if you know about mu, what is the big deal? Mu squared is, but that is not the case here. For example, how to find an, see, we want an unbiased estimator for mu squared. So anybody, we want an estimator such that this is equal to mu squared. Question is, how do you find this estimator? Once you do this, I think the homework is v cubed. So I'm going to show you this. Then you can, anybody, any ideas? So, so suppose you say, I'm going to, this should work, because here look at it, mu hat into x hat. So you know this is certainly not true, right? If expected, this is certainly not true. If expected value of y is phi, I mean, from probability you know that this is not true, right? You cannot square on both the sides. Because that will be, you have to start all over, right? If the expected, if this is delta, I'm saying this is not equal to delta squared, right? So suppose, I'm going to put a question mark, suppose we try this out. So we want to find the expected value of this, this is what we need. Suppose I choose, this is going to be trial and error, suppose I choose that function. Then let's first of all see theta hat, expected value of theta hat. Now, this is where they, you know, remember what is the expression for the variance of x bar? Variance of any random variable is expected value of x squared minus its mean squared, right? So this is expected value of x bar squared minus here. X bar is here, x bar has got mean mu, variance equal to this. So variance is sigma squared over n and minus this. So from here you see that we get this expected value of x bar squared is mu squared plus sigma squared over n, okay, right? Remember, so this will give you an idea. See, remember, we are treating the case where sigma squared is known. So treat sigma squared to be 1. So this is a constant, 1 over n. So from here you see that you can also write like this, right? Alright, so by trial and error, you see this is sigma, this is what I have been looking for because this is a function of the data. So what I am trying to say is this is not good because expected value of theta hat, which is x squared, is not mu squared, but mu squared plus a constant. Because it is a constant, I can bring this to this side. So this is of course mu squared plus sigma squared over n. Consequently, theta hat equal to, or this function, what is it, x bar squared minus sigma squared over n is unbiased for mu squared or theta. Alright, so now what I want to do is I want to figure out whether this is the best estimator or not. So there are two steps involved. So I got an estimator, I got theta hat equal to x bar squared minus sigma squared over n is unbiased. We just found out for mu squared, which is your theta. So the next step is to find out the variance of this and compare it with the the Cramér-Rao bound for this particular theta. So this is generally easy. So let's compute the Cramér-Rao bound. So I need to do two computations. Okay. So very quickly we already have, remember, sigma squared CR for theta. You remember this formula, it's expected value of d log f. You can do it with respect to mu and then d theta over d mu whole square, right? Anybody remembers this? We did this last time. If the parameter is not what you are looking for, you can compute, you can see, you can put it in because, right? By definition, this should have been this, right? Right, that's the Cramér-Rao bound, right? You put here d theta by d, d mu by d theta and then take it upstairs, right? Because this, of course, if I multiply by d theta by d mu, right, d theta cancels. So you have to multiply by d mu by d theta, and that goes at the upstairs as, right, this is true now, right? Because when you bring it down, this comes as d mu by d theta, and this goes out with the second derivative, right? Or so theta is this, so that is 2 mu the whole squared, and we already have this quantity from the previous one. What was it? Sigma squared over n, I think, right? So that's a 4 sigma squared mu squared over n, right? Somewhere here, right? So we found the Cramér-Rao bound easily. This is going to be a little harder. So of course expected value of theta hat is, we just found it, right, is mu squared. So variance of theta hat is right, theta hat minus its mean squared, right? So let me substitute for theta hat. It's all done in the book, so I'm going to be a bit quick. Right? I just substituted this here, so it is this. If you expand this, this is going to be expected value of x4 bar minus This is a standard analysis, right? X minus mu the whole squared is the same as expected value of x squared minus mean squared, right? So you can, right? So you call this to be A, call this to be Y. Y minus expected value of Y minus A the whole squared, right? If A is the mean of Y. Remember, this is the mean of this. So if you expand it, this is a quadratic, expand it, you'll get this. You have a doubt? Remember, this is the mean, so this whole quantity, this is the mean of expected value of x bar squared, right? We did it somewhere else. So when you expand, you will get x4, one term, 2 times expected value of this multiplied by expected value of this, that's square of that, minus the, plus the square of this. So plus the square cancels with 1 minus, and you get minus expected value of x bar squared the whole squared, which is what this is. Now this fourth order moment, rather than do it here, but I'll show you how to do this. So if you want to find, remember x bar is normal with mean mu variance sigma squared over n. So its characteristic function is e to the power j mu omega minus half sigma squared over n omega squared, right? So keep taking the derivative of this. So take the first derivative of this, right? Take the first derivative, then put omega equal to 0. This will be j times the expected value of x bar, and so on, right? You remember the formula? The formula will be, if you want the kth moment of this, then you have to divide, this is the formula. You take the derivative of this function k times with respect to omega, then you put omega equal to 0, divide by jk. So you go home and do it, and I'll give you the answer. So for example, let me do 1 or 2 for you, right? So from here, the first derivative is what? So remember, this whole function multiplied by the derivative of this with respect to omega. So that is j mu minus half sigma squared over n omega, right? Multiplied by 2 omega, 2 cancels. So this whole thing multiplied by phi x bar omega. So when you put omega equal to 0, you get j mu, because this is 1, this is gone. Then you divide by j, you get mu. So you get 1 over j, phi prime 0 is actually mu. This is the expected value of x, which is correct, right? So take the derivative one more time here. So that's going to be derivative of that, so that's j mu minus sigma squared over n omega the whole squared multiplied by phi x omega plus the derivative of this, so that's going to be minus omega squared over n phi x of omega, right? Right? Now we put omega equal to 0, divide by j squared. Omega equal to 0, you see, this is 1, this is 1, this is gone, j squared is minus 1, I'm sorry, so yeah, j squared is minus 1. So expected value of x squared will be 1 over j squared, phi double prime, evaluate 0. So this will come out to be mu squared from here, and here, remember j squared is minus 1. So this minus goes away, this minus goes away, you get this, which is correct, right? Second derivative is that. So I want you to go home and see, you can do this with the fourth ordering. We need the fourth order value, so I'm just going to give you the value. What is it? Somebody can read it to me? 3 sigma 4 plus something. Yeah. So it's mu 4 plus 6 mu squared sigma squared over n plus 3 sigma 4 over n squared. Remember, if this is an interesting by itself. Generally, you know this for zero mean Gaussian. These are the for non-zero mean Gaussian. So the middle one is mu cubed. I mean, third one is mu cubed plus 3 mu sigma squared over n. Well, you see, if mu is 0, of course, all the odd order moments are 0. And so this is the fourth moment. Why do we need it? Because we need it here, right? So if you plug it in here, you want to plug it in here, mu 4 plus 6 mu squared sigma squared over n plus 3 sigma 4 over n squared. Now I'm going to expand this and subtract. Let's see whether we do. So this is mu 4 minus 2 mu squared sigma squared over n, right? Minus sigma 4 over n squared. So mu cancels off. You get 4 mu squared sigma squared over n plus 2 sigma 4 over n squared, right? See, the Cramer-Rao bound is here, so you can see the variance is greater than the Cramer-Rao bound, right? So what is the conclusion here? See, we have an unbiased estimator, but it is not efficient. So the problem is not over. The problem is it possible to get another unbiased estimator with the variance lower than this? So how do we settle this? Okay. So this is the issue. I want to settle it today. So what is the issue? Hello, it's clear it is not efficient, right? Because look at here, Cramer-Rao bound we computed earlier. And so we have this situation, Cramer-Rao bound is here. And we have, see, it's pretty clear because this is the Cramer-Rao bound plus another term. So we are here, this is our variance of our theta hat. So maybe there is another theta 1 which is here. Is it? That's what we want to know. Then this will be a better estimator. And even if you do this, then there may be another best. So we need to come to this UMVUE, which is the one with the minimum most variance. Okay. So let me show you, so I'm going to solve that, we are going to resolve that problem now. But if you are not motivated enough, I'll show you another example. If you didn't, of course you got the point, but so try to go home and redo this for theta equal to mu cubed. Again, you can trial and error, you can find an unbiased estimator, but always find the variance, find the Cramér-Rao bound. Again, you will see that whatever you are coming up with is not an efficient estimator. So then, of course, the question is, how do you find the best unbiased estimator with the minimum most variance? Okay. So there will be some problem of this type in the midterm exam. At this point, if you go into, I already gave you one exam, I think. If we go into my course website, the other one, at eweb.pol, I can bring it to you. There are a few exams I have already posted there. Okay. So you can try to solve them. Right.
The course, there is one from 2006.
Yeah. Right. There I put some exams, EL 6th. But I can bring it to you. I'll just print it out and bring it to you next time. I'm saying it. I can also copy it to Blackboard at this website, right? I think it's in my write-up also. Now, if on April 2nd, April 1st, if you are not ready, we'll do it April 8th. We'll see how it goes, right? So let me do one more example, then we will go into since I want to get back to this, let me just put the result here. So example 1 was, you don't have to write this. Xi's are normal with unknown mu, sigma squared known. The parameter of interest is mu squared. So we had theta hat equal to, if you define x bar as 1 over n sigma xi, then we had theta hat equal to x bar squared minus sigma squared over n is unbiased, but not efficient. Because variance of theta hat turned out to be 4 mu squared sigma squared over n. And that turned out to be greater than the Cramér-Rao bound, which was only the first term. So certainly this is not an efficient estimator. Okay. Just one observation is that our estimator is a function of the sufficient statistic. Okay. So let's look at the example 2, a second example. So there will be one problem to determine the UMVUE in the exam, the minimum most variance. So we'll do this. I think we have done this first one already, right? Theta equal to lambda is the unknown parameter, but this is more interesting. So let's do theta equal to theta 1 is lambda. And remember, anybody remembers what is the sufficient statistics for this? Sum of the xi's, right? Yeah. which turns out to be Poisson with parameter n lambda. Right? How do you get this? So because the joint density function of x1 etc. xn is what? E raised to minus n lambda, lambda to the power sigma xi, right? Over xi factorial, right? So this is your hx, this is your g of lambda of t, yes? So this must be ts, right? So the sufficient statistics is of course sigma xi, which also happens to be Poisson with parameter n lambda. This is where we start, okay? So if I make a guess, theta 1 hat as 1 over n ts, that's 1 over n sigma xi, I equal to 1 through n. Then you can see expected value of theta 1 hat is what? Anybody? Lambda, right? Because each of them is lambda. And the variance of theta 1 hat is what? Anyone? Alright, it's going to be 1 over n squared plus sum of the variances. So n lambda over n squared is n. How about the Cramér-Rao bound? We take the logarithm, etc. Right? So d log p of x1 etc. xn is minus n lambda plus sigma xi log lambda minus logarithm of product of the xi factorial. So if I take the derivative of this with respect to lambda, I should do the derivative here with respect to lambda. So that gives me minus n plus sigma xi over lambda. So if I do the second derivative, right, second derivative is going to be minus n goes away, so sigma xi over lambda squared with minus sign. So its expected value, right? So this is p of x1 etc. xn. So its expected value is, so you can say sigma squared CR for lambda is minus 1 over expected value of that quantity. I think we have done this in the class. So that's its expected value is n lambda over lambda squared, right? So lambda cancels, then with the minus sign you get lambda over n. So this is the same as the variance of theta 1 hat. Bottom line is theta 1 hat is efficient, right? Alright, so let's go to part B. So I need the best unbiased estimator. So let's start with the lower bar. How do we even find an unbiased estimator? Anyone? You should be able to guess. That's not that easy. For example, expected value of, you can take another problem. Maybe before we go into this, let's do 3 problems. Okay, let's do a simpler one. Suppose it is lambda squared and a third one is e raised to minus. So let's do the simpler one. How about lambda squared? Anyone? So we could try, suppose xi is Poisson. Of course, xi is Poisson with parameter lambda. So what is expected value of x? Anyone? X is Poisson with parameter. Expected value of x is lambda. Expected value of x squared? Anyone? Or what is its variance? So this is variance of x plus x. Mean squared, right? So this is lambda plus lambda squared, right? So can't I write this as, so this is a lot of, I can write it like this, right? Lambda squared plus lambda, right? So what am I trying to say? I'm going, what is the expected value of x squared minus x? Anybody? Very good. So remember, if I take that much is true, so when you have nothing to do, you should do a few problems like this. And so we have, let me call y to be sigma xi, right? So this is Poisson with parameter n lambda. So we have expected value of y is n lambda, variance of y is n lambda. So expected value of y squared minus y is what? Anybody from here? Right? Yes? Or you can write this way, right? Right? But you see, now we found an unbiased estimator, okay? Now, so what I'm going to not do the next part. So you should again, because if you consider theta 2 hat to be 1 over n squared sigma xi the whole squared minus sigma xi. This is of course unbiased for lambda squared. I want you to go home and compute, show that this is not efficient again, okay? So let me see whether you can do this as a homework problem. Find the variance, and I want you to show that this is greater than the Cramér-Rao. Cramér-Rao bound is easy because this is derivative of this. Cramér-Rao bound I can do it by hand. My derivative of this is 2 lambda square multiplied by the Cramér-Rao bound for the other one. So 4 lambda squared multiplied by, so it's 4 lambda cubed over n, right? So this quantity is 4 lambda cubed over n. This quantity will turn out to be 4 lambda cubed over n plus something over n squared. I want you to compute what this is. Just go through the computation. And then you conclude that it is not efficient. Again, we have a problem. We have a case where estimator is not efficient, right? To compute the higher order bounds for Poisson, let me give you an identity. So how does this go? Poisson expected, if x is Poisson with parameter lambda, then expected value of x is lambda. Expected value of x squared is lambda plus lambda squared. How do you find you need x cubed, x4, etc. So you can use this result, Chen's lemma, not SK Chen. For Poisson random variables, this is true. Let me show you, first of all, let me prove you why this is true. So the left side is what? Sigma k gk e raised to minus lambda, lambda to the power k over k factorial. K goes from 0 through infinity, right? k gk multiplied by probability of x equal to k. But when k equal to 0 here, the first term goes away. So this is the same as k equal to 1, right? K equal to 0, the first term vanishes. Now because it is k equal to 1, I can cancel this k and make it k minus 1 factorial. Then what? I am going to put k minus 1 to a new variable m. So this summation now reads m equal to, remember k minus 1 equal to 0, so m equal to 0 through infinity. G of k minus 1 is m, so k is m plus 1. So wherever I see I put m plus 1, e raised to minus lambda. Lambda to the power k is m plus 1, so lambda m over m factorial. I pull out the lambda outside. But you see the inside quantity is lambda multiplied by expected value of g x plus 1. Okay. So I just proved this statement. Why is this useful? Look here. So expected value of x cubed is, according to here, lambda multiplied by expected value of x plus 1 the whole squared, right? From here, lambda multiplied, g is what? Yeah, expected value of x cubed can be written as x multiplied by x squared, right? So this is your g. So this is lambda multiplied by expected value of g, you replace x by x plus 1. So it is this, right? Yes? But now this you can do, so this is going to be lambda multiplied by expected value of x squared plus 2x plus 1. Then we can use, so this is going to be lambda multiplied by x squared is lambda squared plus lambda plus 2 lambda plus 1. So you have lambda cubed plus 3 lambda squared plus lambda, right? And so similarly you do the fourth term, etc. So expected value of x4 equal to expected value of x multiplied by x cubed, right? So this is lambda multiplied by expected value of x plus 1 whole cubed. Then you expand it and use these results. So you go home and do this. So this will be expected value of x cubed plus 3x squared plus 3x plus 1. Now you can plug it. So you need all this to put it in here, right? Anyway, I don't remember, but you can, but you will need that to compute the variance. That's my point. So go home and do it. So again, here I found the theta 1 hat equal to x bar. This is efficient. Theta 2 hat is, we have an estimator, right? Where is it? Yeah, here. So I can write this as, watch here. This I can write, y over n is x bar, right? Y over n is this. So I'm going to call this x bar. So if you want, I can write this as expected value of x bar squared minus 1 over n x bar, I think, right? 1 over n x bar. So we have x bar squared minus 1 over n x bar is, and both are, everything is unbiased, but this is not efficient. I didn't do the last step. I am asking you, just go home and you do need to practice something, right? All right, very good. So let me go to the more difficult one now. I'm not sure whether we'll finish everything by April 1. So the exam may be April 8. We'll push by 1 week. Let's see how these things go. So theta 3 is e raised to minus lambda. So we of course need an unbiased estimator to start with. We need an efficient estimator, we need an unbiased estimator with the minimum most variance. So this is why you need to do a lot of problems so that you can use ideas from, see this is difficult. So again you see, just because you know you have solved this problem, generally that is true. If you know, of course if you know the value of x, x squared is easy, you just square it, but that's not the case here. If you know an unbiased estimator for lambda, that's not going to, squaring that is not the unbiased estimator for lambda squared, right? Similarly, if you know the unbiased estimator for lambda, just e to the power minus that is not the unbiased estimator for e raised to minus lambda. So the Cramér-Rao bound for e raised to minus lambda is easy. So that's going to be d theta by d lambda, right? Squared over the, right? What is it? 1 over expected value of d squared log f with respect to lambda with the and multiplied by what I had before, d theta by. So you can also write this as, if you want, Cramér-Rao bound for lambda multiplied by d theta over d lambda squared. So d theta over d lambda is what? E raised to minus lambda with a minus sign. So e raised to minus 2 lambda. I guess this is the Cramér-Rao bound. That's easy. Right? Because this we found earlier, somewhere here. Somewhere here. Lambda over n is the Cramér-Rao bound for sigma squared. Right? So the question is, how do you find an unbiased estimator? Let alone the best one. So I'm going to do a trial and error, okay? So this is of course a silly one, but let's see what happens. See, expected value of z is 1 multiplied by probability of z equal to 1. But z equal to 1 is the same as probability of x1 equal to 0. But x1 is lambda, so probability of x1 equal to 0 is e raised to minus lambda, lambda to the power 0 over 0 factorial. Okay, so we found an unbiased estimator, but we only used one observation. So certainly by all means this is not a best estimator, right? But anyway, for argument's sake we will find the variance of z. So that's expected value of z squared minus its mean. Mean is e raised to minus 2 lambda, right? Expected value of z squared is what? Anybody? So that's the same as, z only takes one value. So 1 squared multiplied by probability of z equal to 1. That's the same as 1 multiplied by e raised to minus lambda itself, right? Minus e raised to minus 2 lambda. So if I pull out e raised to minus 2 lambda outside, then this is e raised to lambda minus 1, right? So this you can write it as e raised to minus 2 lambda sigma lambda to the power k over k factorial, k equal to 1 through infinity, except the first term. What happened to n? There has to be, all right, so in any case you can see that this term is much higher than this. Even with the one observation, this is lambda, here you get this term, right? Because lambda multiplied by e raised to minus 2 lambda. So whatever it is, this is much, much higher than this. So certainly it's not an efficient estimator. There may be better estimators, so there is a whole host of questions now. So you understand the problem, right? So certainly in this case we should be able to find estimators with even lower variance. Okay. So remember, this is much higher than the Cramér-Rao bound for theta. So all this leads to so this is a question. For each problem, how to find an unbiased estimator with the minimum most variance. And this is where our second theorem is going to help, which is Rao-Blackwell theorem. So I'll do the Rao-Blackwell theorem now, and then we will see whether we can find the UMVUE for all these problems. Then couple of problems you do this, and there will be a problem of this type. This is the difficult part. So there will be one problem of this type in the midterm exam, about 40 points, 40 out of 100. So if you don't do it, you do lose a lot of points. So you do want to check out, do some problems at home. That sounds like a title of a movie, right? Finding Nemo. So T of x is the set of all unbiased estimators. So we are going to start with that. Okay, very good. I won't write it here. So all these three estimators are, thank you, unbiased estimators. First one is efficient, so that's all good. These two are not efficient. So we want the UMVUE here. Anybody has any doubt that for a parameter theta that there could be more than one unbiased estimator? Yes? So take the first problem. All the xi's are Gaussian with the mean mu. Give me two unbiased estimators. Anybody? Just unbiased, not minimum variance, unbiased. So theta 1 hat equal to x1, theta 2 1 hat equal to x2 or x1 plus x2 by 2, x1 plus x2 plus x3 by 3. All these are unbiased estimators, but with the different variances. But we found the one with the, in that case we found one with, so certainly for any problem there could be many unbiased estimators. Okay. So that means expected value of any tx, if you pick up a tx from here, if you pick up a tx from here, then this is theta. That's what we mean by unbiased, right? That's just definition. So let me show by S that whole set of unbiased estimators. So we say T naught is UMVUE for theta if for any T in this set the variance of T naught is less than or equal to variance of all the T's. Okay, that's what I have been saying all along, right? Alright, the first thing I am going to show is that such a T naught is unique. So I'm going to prove you the uniqueness of UMVUE. See, here I said that, look at what I'm saying. I'm saying the UMVUE is unique. So first, suppose you don't believe me, so I'm going to show you. So let's assume that UMVUE is not unique. That's what I mean by if not. Suppose that is not unique. So this is where I want to start with. I want to say that both T1 and T2 are UMVUE and they are not equal. So I'm going to show you a contradiction. So I'm saying that, of course, both of them are unbiased, right? So we have this. And we also know that the variance of T1 equals to variance of T2 equal to sigma squared, because that's the minimum most variance. And we also know that the variance of any other T is greater than or equal to sigma squared. Why is this true? Anybody? Why is this true? This has the minimum most variance. So any other unbiased estimator has to have variance greater than or equal to sigma squared, right? So this is the variance of the UMVUE, right? So suppose you choose, look at this, I'm going to construct a new estimator T. So let's consider T. Then of course expected value of T is, as you can see, is theta, right? because expected value of this is theta, so this is unbiased. So this t belongs to this club, right? Let's look at the variance of t. So variance of t is 1/4 of variance of t1 plus t2, right? Variance of t1 plus t2. So that's 1/4 of expected value of t1 plus t2 minus its mean. So that's minus 2 theta, the whole squared. You know how to expand this. Or from here, you know this is variance of t1 plus variance of t2 plus. So I'll show you here. So this is 1/4 expected value of t1 minus theta plus t2 minus theta, the whole squared, right? So if I expand, the first term expected value of t1 minus theta is variance of t1, right? Plus expected value of t2 minus theta, the whole squared is variance of t2, plus 2 times expected value of t1 minus theta multiplied by t2 minus theta. What is that? Covariance, right? That's the covariance between t1 and t2. But remember, this quantity is sigma squared, this quantity is sigma squared. On the other hand, any other variance has to be greater than or equal to sigma squared. Bring the 4 here and get rid of the sigma squared. So you have, so you see, so sigma squared, 4 here, this 4 comes here. Then you have sigma squared, so 2 sigma squared goes. So you have 2 covariance of t1, t2 is greater than 2 sigma squared. So you have covariance of t1 comma t2 is greater than or equal to sigma squared. But on the other hand, you know this, right? Covariance has to be, covariance of 2 random variables has to be less than or equal to their sigma multiplied by sigma, right? From Cauchy-Schwarz, right? This is less than or equal to variance of t1. So this is sigma squared. So to satisfy both these, we need covariance of t1 comma t2 must be equal to sigma squared, right? So in other words, you have this is equal to variance of t1 multiplied by variance of t2 equal to sigma squared. So if the covariance equal to variance, what happens to the correlation coefficient? Anybody? Correlation coefficient is covariance over square root of the variances, right? So that's 1, as you said, right? That means the 2 random variables are completely coherent. That means T2 is of the or T1 is of T2 is of the form AT1. That's what this is the condition for correlation to be 1. Coherent, completely coherent, right? So with the probability of T2 equal to T2 is 1. The 2 random variables are essentially coherent almost everywhere. Why is that? You take this condition, plug it in here, you will get 1. Because when T2 is T1, covariance between T1 and T2 is A multiplied by the variance of T1. This will be variance of T1, so you will get A squared square root, so A cancels, you get 1. But you see if T2 is, so we have T2 is essentially equal to AT1. So if you take the expected value, here you get this is equal to expected value of AT1. But this is theta, this is A theta. So we conclude that A is 1. That means T2 is T1 essentially. So what did we prove? We said if you have T1 and T2 are both UMVUE, then T1 has to be equal to T2. So we just proved uniqueness, okay. So the first result is that UMVUE is unique. I just proved it. And now comes the final result. So we are back to this concept of sufficient statistics that we introduced 2-3 lectures back. Remember what is sufficient statistics one? So the joint density function of xn and theta can be written as in this form. And this T only involves the data. So this is the sufficient statistics. So let Hx be any unbiased estimator for theta. So this is the Rao-Blackwell theorem. So Rao-Blackwell theorem says that if you can find any unbiased estimator for theta, and if you do the conditional mean of that unbiased estimator, condition on the sufficient statistics, whatever you get is the UMVUE for theta. So you understand the statement at least, right? Remember, this is what we have been looking for. So finally you got it. UMVUE is given by this quantity. So there is, so in other words, if things are difficult, what it says is you do it in 2 steps. You somehow try to find so first thing is you need to find one candidate, an unbiased estimator. That may not be best one, but you can make it best, or you can make it best by going through this procedure. Procedure is you need to clean it up. Using, in other words, you take the unbiased estimator and you find it's a conditional mean, but conditioned on the sufficient statistic for that parameter. Then of course the whole thing will turn out to be a function of the sufficient statistics, but whatever is that function, so let me call that function to be like this. It will be some function of what? T, because that's the, right? This function is the UMVUE for the theta. So you see, this is unlike the Kramer-Rao theorem, this is a constructive theorem. You can do the stuff. First let me prove this, then I will use this theorem to solve the 3 problems that we picked up earlier. I am just going to sketch the proof because the proof is there in detail in all the books and in my notes, etc. So this is a big deal in statistics. See, unlike the Kramer-Rao bound, that doesn't tell you how to find an unbiased estimator, or it doesn't tell you anything. It just gives you the lower bound for all the unbiased estimators. Whereas here it gives you a procedure to find the best estimator. In fact, this is the best estimator because this is the UMVUE. UMVUE is minimum variance unbiased estimator. So we have been looking for this. This is your T naught. Remember, T naught is the UMVUE. T naught is unique and T naught is given by this double procedure. So the only catch is you need to know, you need to somehow come up with, this is the catch. You need to come up with an unbiased estimator, but the good thing is this can be sloppy. By which I mean, this may not, its variance may be poor, but then you go through this procedure. So first I'm going to prove this theorem, then we will do we'll look at those examples and see how to make use of this theorem. Okay. And it actually, the correct, you have to add that for uniqueness, you also need the completeness of the family. Okay. Right? That's what we want to show. We want to show that the variance of T naught is less than or equal to variance of any Hx, Hx being a member of the unbiased family, right? What is T naught? Remember, by T naught now I am writing this quantity. So you keep writing this. So we are going to prove backward. So we'll say that this is what we want to show, that expected value of. Remember, both are unbiased, so we need to show that this variance is smaller than this. Remember, variance is random variable squared. So it is this is variance is what? T naught squared minus theta squared. We want to show this quantity, right? Right? We need to show this. Keep writing, we need to show. So this is the same as saying we need to show expected value of T naught squared is less than or equal to expected value of H squared. I thought I didn't bring it. Let me just shut it off. All right, so now let me substitute for T naught. So this is expected value of So what is T naught? Remember, T naught itself is expected value of Hx given T equal to T. So we want to show that this quantity, right? This is T naught, right? Why is that? I just copied from here. T naught is expected value of Hx given T. So there's going to be a little bit gimmicks here. But remember, you also know this one, right? Expected value of y squared can be written as expected value of y squared given x, right? Okay, on any random variable, so I can write it y squared given t, right? So you see this can be written as, so I want to show this is less than or equal to expected value of h squared x, but that's the same as expected value of h squared x given t, right? Using this argument. Right? So this is what we need to show, right? So keep writing that we need to show But you see, if you need to show this, right, expected values like an integration, isn't this true? It's enough to show the inside quantities, right? It is enough to show that the inside quantities satisfy that inequality. So this statement will be satisfied. If you want, you can write the statement will be satisfied provided. So you can say the above is true, that provided this is less than or equal to that. So if we can show this last statement, we are done. And the last statement is obviously true from Short's inequality, as I am going to show somewhere. So what is this quantity? What is the last quantity? It says expected value of something, which is what I wrote, right? That's squared, right? This is the left side, because this is now expected value of h given t the whole square, right? That's the left side. But this quantity can be written as integral h square root of f x given t Oh, I wrote f as square root of f square root of f, which is fine, right? And this, call it ab. So integral ab squared is less than or equal to integral a squared, integral b squared by Schwartz, right? So this is less than or equal to integral a squared integral. But integral a squared is what? H squared f x given t multiplied by integral f. But this is 1. And this quantity is expected value of h squared given t equal to t. This is what we wanted to show. We said if this statement is true, I just showed you that that statement is true. So if this is true, this is true, this is true, we have shown this, right? Alright, so remember, ultimately we wanted to show that the square of that expected value is less than or equal to expected value of the square of h squared, which is what I have shown. Look at here. We showed that the square of the expected value of h given t is less than or equal to expected value of h squared given t. Precisely the last line is shown. Consequently, everything is true. The theorem is true. And you should read there is a bit of discussion on the Rao-Blackwell theorem, saying when do you get equality here, etc. The condition for equality turns out to be that H should turn out to be expected. So this is the condition. So this means if this, remember this will obviously be the case if H happen to be a function of t itself. If H is a function of t, H given t is going to be this H will come outside. Okay. So what is the bottom line? You have equality. I mean, it's proved in great detail there. I'm skipping few steps. So if you read up, the bottom line is you will have equality if your unbiased estimator also happens to be a function of the sufficient statistic. Before we go there, look at, so let's go back to the Rao-Blackwell theorem. Look at what it says. It says the UMVUE, when everything is done, UMVUE is going to be a function of the sufficient statistics, right? Right? UMVUE is a function of the sufficient statistics. So let me write it down here, and I want to bring in a couple of observations to you.
Excuse me, Professor. The start of the proof that the variance of T0 is smaller than the variance of HX.
Smaller than or equal to, right?
Yeah, but
what is the problem? So we just showed that coming over this statement will be true where this T0 is this quantity. So we started with the T0, which is expected value of some unbiased estimator given T. So we showed that its variance is less than or equal to Hx.
how can we know the variance of T0 is the smallest of any unbiased estimator?
So give me any unbiased estimator, I'll go through this procedure and I'll show that this quantity's variance will always beat whatever you started, right? So look at what it says. You come up with an estimator. You say, I have an unbiased estimator with certain variance. Then immediately I do this and I show that its variance is smaller than, so whatever you have, I have a better one. And then I think that's what I was saying. Then if you, to complete the proof, you need the completeness. And with that you can put everything together. But from here it should be pretty clear that, so remember, little earlier we also showed the one with the lowest variance is unique. So if this turns out to be a function of t, then it's also unique. So let me just summarize, let me get a few things right. So you have an unbiased estimator. Then if you, what the Rao-Blackwell theorem says is if you, and then you also have the sufficient statistics, right? And then the procedure is if you do Hx given t, remember, you know, once you do this, whatever it is, this is going to be a function of t only, right? So that's the reason I want to write it like this. This will ultimately turn out to be a function of t, where this t is the sufficient statistics. So this is the UMVUE. That's what the theorem says. This has got the, you start with any unbiased estimator. This procedure will give you one with variance which is lower than, with the lowest variance. And so the bottom line is UMVUE is always going to be a function of the sufficient statistics, right? That's pretty clear. Conversely, you see, suppose just by trial and error you were able to find an unbiased estimator which is a function of sufficient statistics, then what happens? I just told you, if you have an unbiased estimator suppose you have an unbiased estimator, okay. This is an unbiased estimator, but it is also a function of the sufficient statistic, right? Now to find the UMVUE from Rao-Blackwell theorem, we need to do GT conditioned on T, but this is going to be GT itself, right? That means the moral is that if you can find an unbiased estimator which is a function of the sufficient statistics, you are done. This is the estimator with the lowest variance. Look here, this is not a problem. We already know this is a, the first one, theta equal to mu, we know already efficient. So if you come here, we have an, this is sufficient statistics is this, we have an unbiased estimator which is a function on the sufficient statistics. So even though it is not efficient, this is actually the UMVUE. So it is true here, it is not an efficient one, but we don't have to search anymore. Moreover, it is unique. Right? Earlier we proved that it is unique. Remember, in the proof, Hx was any unbiased estimator, and then we showed that this procedure gives rise to a estimator whose variance is lower than anything you started with, and then coupled with the fact that that quantity is unique shows you that expected value of Hx given T is the one with the lowest variance, and it also shows that you can actually start with any unbiased estimator. All roads will lead to Rome because of the uniqueness property we proved earlier. Look at here now, second example. This has no problem because to start with we had an efficient estimator, so that was fine. In this case, we found it is not efficient. But again, look here, the sufficient statistics for this problem, x bar is sufficient, right? Or sigma xi is sufficient. So theta 2 hat, we have an unbiased estimator. So from Rao-Blackwell theorem, this is the best estimator. You are not going to, right? Hello, why are you blinking here? The same argument here, you see. If you can find an, so T naught is unique. Conversely, remember I didn't prove it, but the condition for equality is that Hx should turn out to be a function of T, sufficient statistics, because if Hx is a function of sufficient statistics, Hx given T Hx will come outside, right? Yes? So Hx is, if Hx is a function of T, Ht given T is Ht itself. So if you can find an unbiased estimator which is a function of T, then this is already a function of T. So if you try to do the Rao-Blackwell procedure, you get the same estimator. That's the UMVUE. Consequently, this is the UMVUE to start with. That's the argument, because GT given T, expected value is GT itself. Now, the if and only the condition for equality, I sort of skip the proof right now, but you should read it up and it will turn out to be what I said, which is H should turn out to be a function of T itself. So this is already efficient, I mean not efficient, this is the second one. We know that even though it is not efficient, but the best one, but UMVUE, right? But it is UMVUE. Okay? Yes? Alright, so here comes the difficult part, and this I am going to do it for you, the third one. We have to find, look at this, this is not a function of what? sufficient statistics, okay. So let's see how to do that one. It's not there in the notes, so I'm going to do it for you. Any questions? If you, either the book or notes, if you read up, I show that h equal to what I wrote there, expected value of h given t is the condition for. So the question is, when will you have equality? Okay, you need to, it's all argued there. So if h happens to be, if this, if this happens to be h itself, this is, then you will have equality. But this is the same as saying that if h is a function of t, this will obviously be true, right? So this is the condition for equality. Equality would mean what? You get the UMVUE. So if you get an unbiased estimator, which to start with is a function of the sufficient statistics, that's the UMVUE. That's the bottom line. So the moral of the story is, so you can see the crucial role the sufficient statistics plays. So if you can get an unbiased estimator in terms of the sufficient statistics, that's the best estimator in terms of the lowest variance. You do need this theorem, otherwise that result is never clear, okay. I mean, that statement cannot be proved without the theorem. What I said you can see from here itself, right? This is the UMVUE, that's fine. What I'm trying to say is, this is what I'm saying. Suppose a GT is unbiased. A GT means an estimator for theta based on the sufficient statistics. Remember, T is the sufficient statistics. Then UMVUE is given by, look at here, UMVUE is given by, from Rao-Blackwell theorem, GT given condition on T equal to T. But since GT itself is a function of T, this will turn out to be GT itself, right? That means what? The UMVUE is the same unbiased estimator. So any unbiased estimator which is a function of the sufficient statistics is UMVUE. So these cases are simple because we were able to find a unbiased estimator which is a function of the sufficient statistics. Same thing here. When you do mu cubed, you can do the same thing. You can actually use the sufficient stat. So if you can find an unbiased estimator, you are done. But not this. So I'm going to do theta 3 for you now. I have the homework. I have the solutions to homework 4. And please take your homeworks. I did bring all the homeworks you have submitted. Couple of sessions. So there are a couple of them for you. Solutions for 4 is here, which you can pick up when you get up. And homework 5 is here. So equality, you go, you put equality, you go back, you come to this statement. You need h equal to this one. remember we had asked this. So the procedure is find any unbiased estimator for theta, say hx, right? In other words, expected value of hx is theta. So that's your first step. Second step is find sufficient statistics for that problem. So that's Tx equal to T, some function of data, right? And third step is find the Hx given T. So this is your UMVUE, and that will be a function of the sufficient statistics. So of course, in the very first step, if you are able to find an unbiased estimator which is a function of sufficient statistics, you can go home, done, right? What I am saying is if this H also happens to be a function of the sufficient statistics, then it is UMVUE and you don't need to do the third step, right? So this is the procedure. In the first two examples that was the case, but in the last example we have to do the third step. So this is the hardest problem. So you have to practice out few problems. I'm going to show you one hard problem right now, and then I think if we have time we can look at the modified Cramér-Rao bound. Remember, saying that the variance is of some theta hat is greater than sigma squared CR. So we have two statements. Variance of theta hat is greater than sigma squared CR. Variance of theta hat is greater than. Which one is better? Which one is the better bound? Anyone? MCR is another number I have written here. One modified Cramér-Rao bound is here. This is the Cramér-Rao bound. Which is a better bound? Anybody? Huh?
The modified.
No, the top one.
The top one, CR1.
Remember, what do you want the variance to be? So which one is the, out of these three variants, which one is the best bound? Say, I say. Hello?
The lowest value.
Think again. The variance is greater than 0 is meaningless, right? It's always true. So even though this is a bound, this is of course true, right? Look, if I say the variance is greater than, that means the variance is somewhere here. So the best bound is this one. What happens is I'm going to show you problems, maybe not today. This is sometimes, of course, in simple problems it is easy to compute. So when this becomes difficult, you go for a sloppier bound. Advantage is you may be able to compute this. You will, when in situations where you cannot compute this. That's what it is. Of course, if you can compute this, you won't go for an inferior bound. Okay. If you cannot compute this, of course you can make a statement like this. So we'll come to this later. And this is, I think, there. In communication, especially if you are working in any non-trivial problem, finding the Cramér-Rao bound may be tough. In such situations, you do the modified Cramér-Rao bound. All right, so let's go to the third problem. Remember, the problem is we want the UMVUE for the best unbiased estimator for theta equal to e raised to lambda. So this is my problem. All the xi's are Poisson, and theta is what I am interested in is e raised to minus lambda. I know that this hx is unbiased for lambda, right? We already found it. So I have an unbiased estimator for not lambda, for e raised to minus lambda, right? But that's not UMVUE. So its UMVUE is given by so this is, as you can see, this you are not going to do by guessing. So by Rao-Blackwell theorem, this is given by the conditional mean of hx given t. But t is, what is tx here? So we have it, right? Tx is sigma xi, right? xi equal to 1 through n. And it's if you have done the probability, if you add up independent Poisson random variable, this is Poisson with parameter n lambda. So let's find the UMVUE for theta hat. So let's so hx is z, right, given tx. So z only takes one value, luckily. So this is one. I am going to do the computation now. Remember, this is the theorem. Now how to do problems. So you must practice out few problems. Let me see the homework. Let me see whether I gave you another one. If not. You don't have a good problem here, so I will give you one. Because all this you can quickly do it using, but this is a hard problem. So this is going to be expected value of z equal to 1 conditioned on tx equal to t, right? Using probability. So but z equal to 1 is the same as x1 equal to 0 conditioned on tx equal to t. So tx is the same as sigma xi I equal to 1 through n equal to t. So look, this is, fortunately this is A, this is B. So that's the same as probability of AB, x1 equal to 0, and sigma xi equal to t, I equal to 1 through n, divided by probability of sigma xi equal to t. So look at the top line. This is the same as probability of x1 equal to 0. Look here, if x1 equal to 0, then sigma xi I equal to 1 through n is the same as what? Anybody? It's xi from, but I equal to 2 through n, right? Equal to t. So a problem like this will test your probability skills as you. But you may ask, but look here, this is still 1 to n. Why did I do all this? Look here. Here I have the random variable x1. Here I have the random variable x1 through xn. Look here, right? So these two random variables are now not independent. But if I write here, I have the random variable x1. Here I have only x2 through xn. So these two random variables are independent now. So you can write it as the product of the random variables. So this now becomes a probability of x1 equal to 0, probability of sigma xi I equal to 2 through n equal to t over probability of sigma xi equal to t, I equal to 1 through n. But the first one is e raised to minus lambda, right? And look here, this is what? These are independent Poisson random variables 2 through n. So what is it? Also Poisson with parameter? Huh? Right, so this is Poisson with parameter n minus 1 lambda. How about this? Poisson with n lambda. So let me substitute. So Poisson with n minus 1 means e raised to minus n minus 1 lambda. N minus 1 multiplied by lambda to the power t over t factorial, numerator. Denominator is e raised to minus n lambda to the power t over t factorial. So e raised to minus n lambda cancels, t factorial cancels, so you get n minus 1 over n to the power t. So this is 1 minus 1 over n to the power sigma xi I equal to. Believe it or not, this is the best estimator. How would you guess this, right? So this is only through Rao-Blackwell theorem. So this is the UMVUE for so this is the UMVUE for e raised to minus lambda. So let's find it. So what is its mean? Anybody, what is the mean of this random variable? After all this? Right, it is, of course, by design it must be, we can check it. So let's check the expected value of theta hat. So this is same as expected value of 1 minus, what is it? N minus 1 over n to the power t, right? So this is sigma n minus 1 over n to the power k, probability of t equal to k, right? But k goes from 0 through infinity. So this is sigma n minus 1 over n to the power k, e raised to minus n lambda to the power k over k factorial. So n to the power k cancels. E raised to minus n lambda is constant. Here you have n minus 1 lambda to the power k over k factorial. This is the expansion for e raised to, right? So this is e raised to minus n lambda, e raised to n minus 1 lambda, right? So n lambda cancels and you get e raised to minus lambda, which is good. So of course it is an unbiased estimator. As the last step, let me also find the variance. I don't need to do anything. I know this is the best estimator, right? So if you want to, let me find the variance, then I'll give you a problem for you. Or if you look at the homework, exams, I think there are non-trivial problems there. So remember, if you get lucky and you can find a estimator, unbiased estimator, in terms of the sufficient statistics, you are done. Trouble is when you get into situations like this, you cannot find an unbiased estimator in terms of sufficient statistics, but you are able to find a sloppy estimator like here. But then you have to go through this procedure, and that you need to do correctly. So let's find the variance of that. We definitely know there is no efficient estimator here. How will you know? We will have to. We can compute the variance and compare with the Cramér-Rao bound. If they are not equal, we know that this is, you have done the best you can. Okay. So variance of theta hat equals the second right moment minus the mean squared. That's this, right? That's the square of the mean, right? So to find the second mean, we can proceed exactly the same way, right? So this is my own example, so it's not there in the notes, but now you have it. So this is sigma expected value of, what is it, n minus 1 over n to the power 2t, right? That's the square, right? I mean, remember all this, ultimately this turned out to be n minus 1 over n to the power t. So we square it, we get that. So expected value is k equal to 0 through infinity, n minus 1 over n to the power 2k, probability of t equal to k, right? So this is sigma k equal to 0 through infinity, n minus 1 over n power 2k, e raised to, remember t is same thing, right? E raised to, t equal to k is here, so e raised to minus n lambda to the power k over k factorial. So 1 n cancels, e raised to minus n lambda goes outside, summation Is this right? N to the power k cancels, so what do you get? Then what? Yeah, so we can take this inside here, right? So we can write this as n minus 1 squared over n lambda, right? So this is e raised to minus n lambda, then e to the power this quantity. What is it? N squared minus 2n plus 1 over n multiplied by lambda. So e raised to n lambda and minus m lambda cancels. So you get, what do you get? Minus 2 lambda, then? Lambda over n, right? This is only the second moment, minus this, right? So we just computed this. Let me substitute it here. So this quantity is e to the power minus 2 lambda, e raised to lambda over n. So if you do this, e raised to minus 2 lambda goes outside, then this can be expanded as 1 plus lambda over n plus lambda over n squared 2 factorial, etc. minus 1. So this is sigma lambda over n to the power k over k factorial. But k equal to 0 cancels, so k equal to 1 through infinity. And we had the Rao bound somewhere here, right? I don't remember, but I had computed it before, and you can do a term by term comparison and figure out, Rao bound of course is easy, right? So sigma squared CR is e raised to minus 2 lambda over n, right? Look at here, this is just the first term here. So the variance is lambda over n plus lambda squared over 2n squared plus lambda cubed over 3 factorial n cubed, etc. So this is the Cramér-Rao bound, just this first term. So the variance here is clearly higher than the Cramér-Rao bound, right? So it is not an efficient estimator. Hello? It's not an efficient estimator, but the best you can do, right?
As it seems if n is large, we still do good work.
If n is large, remember, of course, if n goes to infinity, you don't have to worry, because Cramér-Rao bound goes to 0, this goes to 0, but then you have to live that long to collect all the data. So the key is always finite sample, what is the best you can do. If you are given a lot of samples, infinite number of samples, then anything is fine. First of all, you will be dead before that, right? No, remember, the one is asymptotic study. You say what happens when n goes to infinity. See, n goes to infinity, we can all go home. Because look, n goes to infinity, the Cramér-Rao bound goes to 0. N goes to infinity, even this goes to 0. That means everybody will do well. But finite data analysis, generally you have finite data. What is the best you can do? Conversely, this will tell you, if you say that I don't really care about error being less than something. If you equate this to something, you can solve for the number of samples required, how much data you should collect. Remember, data collection may be expensive. You don't want to sit around and collect data for a long time. In fact, that data may be useless, because you sit and collect data, you are collecting garbage, because the actual, whatever is the incident you are looking for comes and goes in a short time. So if you want let's try this problem. But without trying, don't come and ask me for solutions, but let me see. How about, same, you can proceed a similar way. How about finding this one? Same problem, but the unknown is e to the power minus 2 lambda. So what is an unbiased estimator? Yeah? Something similar to you said last time. Right? Anybody? Right. And right. So then now you need to take and put the probability stuff and put everything and find a. So my question is, find UMVUE here. How will you answer yes or no? To answer this, you need to compute two quantities. You need to compute the variance of your theta hat, right? So this is where a lot of computations come. You also need to compute the Cramér-Rao bound for this case. And then compare, of course, you have to see whether equality or strictly greater. If it is strictly greater, this is not efficient. And so I don't want you to guess, you have to compute this and show. Right? So this really has two parts. Find the variance of this, because the mean is, of course, the parameter. Then find the Cramér-Rao bound and show that the variance is worse than the Cramér-Rao bound. Consequently, it is not efficient, but the best you can do. So you see, there is a complete solution, right? If nothing is nothing is hanging in here. If you are looking for unbiased estimators with the minimum most variance, the problem is over. It's just a question of doing it. The Rao-Blackwell theorem gives you the best estimator with the minimum most variance. So now the challenge is, any of you, if you can apply to a non-trivial problem, something you are working, and show that this is the best estimator, you can see even a problem like this is quite hard. Now you take a real communication or something problem, Just because you find the maximum likelihood estimator, that may not turn out to be unbiased. But you find the sufficient statistics and then fool around, but then ultimately you can use the Rao-Blackwell theorem. So what I am going to do in the next class is do still a little more complicated problem. So that's the taxi problem, but I'll take you through that. Then we have few more topics in, if you want, I mean this, of course, at the very least I should do multi-parameter estimation. Suppose you have two unknowns at the same time, or you have a stack of unknowns at the same time. So how do you deal with all of them at the same time? Remember, so take this case, we'll wrap up in few minutes. So one problem is this one. You have two parameters, but here theta 1 hat is unknown, theta 2 hat is known. In case 2, theta 1 hat is unknown, also theta 2 hat is unknown. So you need two estimators here, right? Theta 1 hat, theta 2 hat, unbiased. Here you only need one unbiased estimator. This will have some variance, right? So this is case 1. This is case 2. So here you will have some variance for theta 1 hat. Here you will have variance for theta 1 hat and variance for theta 2 hat. So it will be interesting to compare this variances with this variance, right? Which one do you think will be worse? Common sense says because you have more unknowns here, you may not be able to do any better than here. But we want to also prove that statement. And there may be some situations where just because you have a second unknown doesn't mean the first unknown becomes inferior. So we want to figure out those cases. So this is multi-parameter estimation. I will only go a little bit because then you need some matrix algebra, this and that. But at least then we can go improvements on Cramér-Rao bound. So there is another avenue to go. Again, I won't go there unless any of you have interest. If some of you have interest in any of this, you can pick up this as a topic for your presentation also, right? But this multi-parameter, at least we should do a little bit. And so I will go through that after I finish the taxi problem. So if I finish all that by next week, then we will have the exam. But if you try all the homework exams, all the previous exams, and if you cannot do them, then you please ask me, we can do in the class, and if you need one more week, that's fine. Because after the exam is over, you do poorly, then I'm going to count those points, okay? So other one, you can make up your own problem. Say for example, xi's are geometric random variables with parameter p. That means probability of xi equal to k is pq to the power k equal to 0, 1, 2. I think I gave you this problem. Find theta is p. So what we want is the So try this problem, right? So theta is p. P is the only parameter. I want an unbiased estimator with the minimum most variance. If you can find an efficient estimator, fine. Otherwise, find an unbiased estimator, go through the Rao-Blackwell procedure, find its variance, find the Cramér-Rao bound, see whether they are equal, then it's an efficient estimator. But if you get lucky and you are able to find an unbiased estimator in terms of the sufficient statistics, then that's done, right? Nevertheless, you need to compute the variance and Cramér-Rao bound and check it whether they are equal or not. So you could do this problem, but without doing, don't come back. And so I'm not going to give you solutions of this unless you do it. This is easy now since I did the e raised to minus, so still needs a little bit work, but you can do that.